Ay, oo nga pala. What's up everyone? Hello! It's your boy, the one and only Sir Patrick of the Department of Biology. Well, first of all, I'd like to welcome you all for our Bio 110 Systematics class. And I'm doing this right now because I'd like to tell you that Sir Dane decided not to upload the full audio recordings for our first two lectures. Because it seems that he said that these two would actually be just a recap or summary of our reading assignment in our course guide. So, yeah, do not upload those lectures, but I know that some of you expected audio recordings of the lectures, so here I am, doing the lectures for you. But don't worry, Sir Dane will come back for the audio recordings for the third and fourth lecture instead. Okay? So I hope you enjoy this, and once again, welcome to our class. So our first lecture is titled The Science of Taxonomy and Systematics. The first thing we need to address is the difference between taxonomy and systematic, because these two are not entirely the same. Some of us might have this preconceived notion that these two are exactly the same, which is totally the opposite. So taxonomy, right here, is mainly focused on describing, naming, and classifying organisms. So that's the main goal of taxonomy. What do taxonomists really do? First of all, they are responsible for the discovery, description, and naming or classifying organisms, both living and those recently extinct taxa or species. They are usually involved in the documentation of this living world or the natural world around us. Taxonomy usually use this universal or internationally accepted system of naming for certain species. There is this rule that everybody has to agree on for naming organisms. Okay? They are there to make sure that the knowledge and understanding of biodiversity is somehow organized and can be accessed. So taxonomy, we can say that taxonomy boils down to humans, hidden desire, of subconscious desire to box things up, to organize, kind of like a person with obsessive compulsive disorder. Okay? So that's taxonomy. And for me, I really appreciate taxonomy. I mean, I love organizing stuff. But systematics, on the other hand, is the study of nature, according to Myers, the study of nature and origin of the natural population of living organisms, both present and the past. So that's systematics for Meyer. For Wheeler, he said that it is the production of cladograms that link taxa throughout their observed variation. Because in systematics, cladograms or trees, kind of like those trees of life, that we always see in movies. That's what systematic is usually concerned with. Creating this link between organisms across different regions of the world. We tend to create this connection. That's what systematics do. So cladogram, that's one point here. And I'd like you to focus on this triad, because systematic is the conceptual and procedural relationship among these areas or this field. First is taxonomy, of course, because it is a branch of systematics. It is under systematics. So taxonomy is important in systematic. This is what I call the triad, okay? So we have taxonomy here, we have the study of the process of evolution, and here we have the study of phylogeny. So this triad is very important for systematics, for us to create these relationships among these different areas, for us to create this narrative, because that's life, right? we tend to create narratives and story about how life goes, about how life was this, how life was that. So taxonomy is important in systematic because it provides us with the names, no? The categories, the boxes that we put organisms in. We tend to identify them and we try to classify them into these boxes. The next one is the study of the process of evolution, wherein we have the sources of variability or organization, no? This genetic variability within population, because this is the growing part, no? This is the most exciting part about systematics. We use this process of evolution as a way to differentiate different population and to create these certain changes and this speciation through reproductive isolation and, of course, most of all, the natural selection, the origin of species, the hybridization of organism. So the study of evolution is actually interesting for systematics because only in the light of evolution that we tend to create this story about us, about the organisms and the species around us. That's the power of evolution. Okay? So it's a very important part of systematics. The next one is the study of phylogeny, wherein we tend to see the divergence or development of different groups, both in the parameter of time and space and the how this happens. So the study of phylogeny is actually very important for systematics because here we always use cladograms or tree of life. So that's how systematics is used. Okay? So just like for taxonomists, what do systematists do? Okay? So the first one is biosystematists study the big picture. The diversity of living organisms on Earth, all those billions of years of evolution that led to these certain variations, these certain species. You yourself is an amazing story. If you look at it, a person, an extant member of any species, the Homo sapien lineage, is actually a long story of this evolutionary tree. We are this extant taxa. We are a representative, a terminal species of this connection, of this story of life. So it is actually something to live for. We are this extant member, a terminal species. Yes, and it's also a way for us to thank our ancestors, what they did, how we came to be like this. So that's the big picture of biosystematics. We seek to also ensure that this classification of organisms that we see are actually based on evolutionary relationship. Because only in the light of evolution that all of this will make sense. That our story in this world will make sense. And of course, systematics also predicts how certain properties of organism or certain traits is important. No? We can actually predict characteristics of organism. Because, for example, where the first heart evolved, no? We can create prediction about traits. Like what organism contains four-chambered heart across different mammal groups? Or where did the eyes, no? When you talk to a creationist about God, you will always hear that the eye argument, no? Because if you look at your eyes, no? Especially those people with very big and beautiful eyes, if you look at them, you will be in awe. You cannot fathom how evolution did that, no? it always seems that there is this being that designed the eye. But that's not actually the case. If you create these different simulations of how different organisms would tend to evolve an eye, if nature would require them an eye to evolve, and this simulation would predict that there would be hundreds and hundreds of instances where an eye looking apparatus would evolve from a simple light sensing organ. So that's how it is. This simulation actually predicted that since the evolution of an eye is actually important and there's a need for an eye for survival, different organisms would tend to evolve eye. Well, in the simulation. And that's what we're seeing right now. We see that there are different eyes across these different organisms. And there are many iterations or evolutions of this eye. From the simple light sensing organ of the spiders or your protist that can only sense when there are light or no light, to our eyes, to the eyes of cats, birds, and goats, to the eyes of octopus. Because if you ask me, the most beautiful eyes or the most efficient one that is out there are those from the octopus lineage, because their eyes does not contain any blind spot. That's a perfect one. But all of these are not perfect. Even our eyes are not perfect, because evolution tend to create these variations and these different apparatus. So yeah, we can allow predictions about the properties and traits of organism. Like for example, how a certain compound, anti-cancer compound, can be found in a certain family of plants. For example, paclitaxel from the taxol plant. Or how certain anti-pain medicine can be extracted from the snail poison called conotoxins, which are way more powerful than those in the market like morphine. And that's how precisely taxonomy and systematics is useful in science. But I tend to get a bad rap when it comes to utility, no? Because there is a certain, utilitarian aspect from it. For me, as a conservationist, I don't like to protect something because they are useful. Utility and utilitarianism only tends to, leads to globalization or the unregulated consumption and commercialization of everything, all in the effort to satisfy the need of the large but very few conglomerates, corporations, or company, at the expense of environmental destruction and the livelihood of the few. We put price in everything, no? For the glory of the economy, as we say. But this is exactly how our current environmental crises are increasing. The problems of our generation: plastic pollution, climate change, sea level rise, white sand beaches, things like that. It's really bad, no? That's how utility tends to fuck the world, no? But that's just me. If we look at systematics and taxonomy on a usefulness utilitarian perspective, we can see that it is a way to feed the world, study of the pests and pathogens, how to cure them, these biological agents, and improve the yields, and also for discovering the drugs of the future. Just like I said, especially the pharmaceutical industries tend to overly use our natural resources just for the benefit of the bucks, the money, and also for improving human health, for the diseases, and so on and so forth, and actually for enabling industrial innovations, for fuel, creation of plastics, medicines, things like that. But, I mean, if you look at this, it is useful, no? But I think its usefulness should not be a basis for the merit of the field, because there is something more important than this usefulness. This field, systematics and taxonomy, has an intrinsic value to it, if you know what I'm saying. That no matter how useful it is, it won't match that intrinsic value to the subject. And if you really love the subject, you really like to classify things, you won't need these uses, no? This utilitarian aspect to it to justify why we do systematics and taxonomy. And yes, we'll also talk about sustainability, because systematics and taxonomy are the forefront or the initial stages for sustainability. Because if you think about it, if you don't know what you're protecting, you can't protect it because you don't know what it is. So yeah, but when we talk about sustainability, what can you guys think of? Sustainable, of course, sustainability, duh. But what is it really? Well, the most important part about this word is, well, putting it simply, is how we use or how our current consumption of resources would not compromise how the future generation would use it too. For example, the clean air that you're breathing in right now, come on, breathe in, breathe out. Inhale, exhale. That's right. How we use this air right now, how it smells, how fresh it is, so that it should be the same air, that same quality that our future sons or daughters would breathe. That's sustainability. And that's why systematics would also help in exposing the threat from these different human-induced environmental changes. Just like I mentioned, global warming, pollution, and all those extractive industries. Moving on, in keeping up with our utilitarian narrative, of course, our field would also be important. It will act as a supporting character to other fields of sciences. It's actually very important for these fields of sciences. In ecology, by ensuring that species and other taxa are scientifically robust, well characterized, and actually accurately identified. Because just like what I said, it is the initial part of the study of ecology. You need to identify. If you don't know what organism you are studying, you can't study them. And especially in ecology, since we usually create this link, this story about the interaction of different species and the environment around them, if we don't know the names of this organism, we will just name them miscellaneous species 1, species 2, species 3. That's the real sad part if you don't know systematics when you study ecology. And also for genetics, by providing the evolutionary and taxonomic framework that allows the understanding of this genetic diversity and evolution. Like how certain finches species diversify through adaptive radiation into different species with different big sizes. And also for geology, by characterizing and documenting the different fossil, yes, that would be a basis for those tons and tons of stratigraphic records. And of course, for mining and oil and gas exploration, because there are certain species that are key indicators of certain reserves, oil reserves, or minerals, something like that. Okay? And for earth sciences too, by enabling the documentation of different organisms that are part of your biogeochemical cycles. So these biogeochemical cycles are actually important for the whole system of the earth, because these biogeochemical cycles is what makes the world go around. It pertains to the biotic, the living, and the geological as well as the chemical processes that happens in the earth. And since there is this biological processes, of course, taxonomy would be important to that. Also in oceanography, by discovering, documenting organism, this is actually interesting part too, because, well, as people, no? As humans, we have explored the moon far better than we explored our depths. No? Those deep, very deep trenches, those oceans, those things underneath. There are these species that are totally alien-like amidst our home on Earth. Alien-like species and organism deep in the deep sea. But we can't know them, no? That much because we don't have studies. But taxonomy and systematics would really be important to that. Okay? Also for climate sciences, by enabling the past and current future climate change to be tracked through understanding its effect on the species and the ecological communities. How different organisms tend to increase or decrease, or how certain patterns of the numbers of organisms are affected by climate changes. No? And as you can see in the figure here, and yes, we humans have caused the 6th mass extinction. And yes, we are in the current Anthropocene period. Kudos to us. For our agricultural sciences too, by characterizing the pest, no? Mainly this is focused on production of food for us, no? Crop plants, and so on. And yes, as I mentioned, in medicine too, for us to have a deeper, more accurate knowledge of the microbiome, the pathogens, the antibiotics and probiotics, things like that are inside us, around us, for the extraction of different compounds as anti-inflammatory, antibiotic, anti-cancer, anti-everything. That's medicine. And also for environmental science, by discriminating species and supporting an understanding of the life history and management of natural resources. Systematic would be important, and taxonomy would be important to this environmental science, because most of these environmental scientists rely on the identification of organisms for their data. Okay? And last but not the least, for conservation science. And yes, as a conservationist, I would agree, because just like what I said, you can't protect what you don't know. A wise man once told me, you can't plan anything. The first thing you have to do is identify that organism you want to protect. If you want to protect that organism that you really love, you first have to know them, di ba? Parang si Crush. Kailangan mo muna silang kilalanin bago mo sila mahalin or protektahan. Something like that. Okay, for the last part of our lecture, we'll focus on the brief summary of history of the science of taxonomy and systematics. As we can see from the readings in our course guide, the development of the science of systematics and taxonomy took a very long time. Actually, it developed from the prototype to the mature type along the span of 24 centuries. So, starting from the golden age of the Greeks in the 4th century BC, from the likes of Plato, Aristotle, and Theophrastus, to the Renaissance in France, in Europe, by the works of Cesalpino and Magno. Yes, the French. To Ray and Linnaeus, the father of taxonomy. He was really a prolific boxer, if you ask me. He really liked to classify and organize and box things up. If it wasn't for his practical and orderly genius that have early on grasped the need of biology for an order with the things that we study, we wouldn't be here in the first place. So if you think about it, he is the one to blame for this course. Curse you, Linnaeus! You're the vein of our existence. And of course, the likes of Comte de Buffon to Anderson in the early 1700s and early 1800s, with the experiment on biogeographical descriptions of some islands. And then come the 19th century pre-Darwinian up to Darwinian Enlightenment, as I call it, wherein with the help of this German scientist Darwin and his English partner naturalist Wallace, well, not technical partner, but pen pal, they have developed Darwin's Origin of the Species. At this point on, we have come to a more or less familiar ground, because this part is the part where the super famous Darwin comes along. Indeed, the 18th century progress had matured into the 19th century evolution. The most pivotal part of the 19th century, I think, would be the development of the so-called biological concept, which played an essential role in the understanding of systematics and the evolution too, and the whole of biology. Even if one cannot apply this concept in some particular cases, still, it is a great benchmark for what really a species is. We will discuss more of this on the next lectures, in lectures 3 and 4. So, just pin this in your head, in the top of your head, for quite some time until we get back on it. Okay? So yeah, to sum up, please remember this. The present day systematics is a fascinating science. It is a synthetic science that derives support from many sources or fields, just like biogeography and conservation biology. This is a growing trend in most fields nowadays. It's either interdisciplinary or it's multidisciplinary, which gives the field a completely interesting and new dimension to it. Like how advancement in molecular genetics has transformed or revolutionized how we see evolution and the science of classification. And yeah, that's all for today. And if you have comments, questions, and suggestions, we have the comment box down below. And if you like it, please do leave a thumbs up. And see you again for the next lecture. This is Sir Patrick signing off. Peace out.